You're on the Argmin video channel, minimal value math videos for frustrated mathematicians. This is a real analysis video series, lecture 13 on closed sets and closures. So closures and closed sets are a very important topic in real analysis and are very useful for future studies of topology and limits and geometry when you talk about holes, punctures, or bounding. So let's define what closed and open mean, but first we need to know what a limit point is. It's a pretty intuitive definition. Let A be a subset of Rn, or we say X in Rn is a limit point of A if there exists a sequence of ANs in Rn they have to be an A such that AN goes to X. So one thing to note here is that the X has to be in is in Rn and not necessarily in A. So you can have a limit point that's outside of a set. So let's look at an obvious example of limit points. Every point A in A is a limit point of A. So A, if you just take the sequence of A's itself, that converges to A, so we got that's a limit point. The only thing that has to be in A are every element in the sequence. So let's look at an example where it's a bit less obvious. So let's take an example in R, A equals 0, 1, the open interval between 0 and 1. And look at the series 1 over n plus 1 as n goes to infinity. This goes to 0, but 0 isn't in A itself, but is still a limit point of A. Another example, every X in R, the real numbers, is a limit point of the subset of R, Q, the rational numbers, and we showed that before, how to construct such a sequence. Now let's get on to the meat of this lesson. We say a subset of Rn is closed if A contains all its limit points. So for example, just some convention that we're going to use, the empty set is closed because it contains all of its limit points, i.e. nothing, and Rn itself is closed because a limit point has to be in Rn, so it's just sort of a circular definition. Now let's take another example. The set of rationals is not closed because you can construct a sequence of rational numbers such that Qn converges to pi, i.e. if you just add a digit of pi for every new rational number. And pi itself isn't rational, so the rationals are enclosed. And the open interval is, big surprise, not closed, since the sequence 1 over n plus 1 has limit 0, but that isn't in 0, 1 itself. Now the closed interval is also a big surprise, closed itself. Let's show that. So let x in R such that the sequence xn has limit x for some sequence in the closed interval 0, 1. Each xn is in 0, 1, and so x will be in 0, 1 since limits preserve order. That's just saying if every element is in a closed interval, then the limit itself will be a closed interval, which is a property of limits known as limits preserving order. Some more examples. In R2, if you take a 2-tuple that satisfies x squared plus y squared is less than or equal to 1, that's just the closed ball, which is closed. And you can do that with a similar argument as the previous one of preserving order. And if you take any r greater than 0, the ball B of radius r0, centered at 0, is equal to everything in Rn such that V is less than or equal to R, and that is closed. So just generalizing the previous example of the closed ball. Why? Because if you take any sequence in the set and suppose it goes to x, since it goes to x, it must be that xk goes to x, which is just a property of limits that we don't talk about, but you can look it up. So if the vector converges to x, then the norm of that vector converges to the norm of x. Since 0 less than xk less than or equal to r for every k, it must be that every norm is in 0r as well. And just to spell that out a bit more, xk is in a closed interval 0r. So using that property we used before, that limits preserve order, i.e. if every element in the sequence is in a closed interval, then the limit itself is in a closed interval as well. And another generalization that we'll just state, not prove, if you take the ball of radius r around a vector v, so instead of being centered at 0, it'll be centered at v, and that's defined as this. x minus b less than or equal to r is also closed. Now let's look at some properties. If a and b are a sequence in R, are a subsets of Rn, are closed, then their union itself is closed. Proof. So let's assume everything that we're given are closed. Now let's construct a sequence in the union such that it has limit x in Rn, not necessarily in A and B. Then, without loss of generality, we can say there are either infinitely many xk's in A, or it could be in B, but we're just going to assume it's in A without loss of generality. Therefore, there's a subsequence. And just to say a bit more about why this is true, it's because every element in the sequence is in the union, and it's an infinite sequence. So there should be an infinite number in either A or in B. There's a subsequence that only exists in A. Since xk goes to x, the subsequence must also go to x. Since xkl is a subset of A, and A is closed, x itself is in A. Therefore, x is in the union A union B, completing the proof. As another example, if you take an arbitrary number of closed intervals, or closed sets, then their finite union is closed. And the proof just uses induction on the previous proof. As an example, if you take an infinite union, this doesn't hold anymore. So if you take these closed sets from 1 over n to 1, that converges to an open interval on the left, which is not closed. So infinite unions don't work. If I is a set and AI is closed for all I in I, then the infinite union, or possibly finite, doesn't matter, is also closed. That's I in I, not in Z. Proving this, suppose AI is closed for all indices in this index set, I and I. Suppose we have a sequence in this intersection that goes to some x in Rn for each I. We have that xk is in each I, and since AI is closed, X itself is in AI because each AI contains its limit points. Therefore, each element is in the union. So for example, if you just take a single set or a single element set, it itself is closed. X. So any finite set is closed. We're just moving along here through a bunch of properties. Looked at unions, intersections, and finally finite sets. Why? Because if you take any finite number of sets and take a finite union, then since it's a finite union, it itself is closed. Closed, finite union, closed. And each of those are closed because the only sequence you can create out of a single element subset is just the sequence of single elements itself. Okay, that's the properties of closed sets. Now let's talk about something called the closure. So let A be a subset of Rm. If the closure of A, which we'll write as A bar, you might have seen notation similar to this for the complement of the set, but we're going to use different notation for that. We're going to use A bar for the closure, which is a pretty standard notation in analysis. A bar, the closure, is the set of limit points of A. Closure of A bar. And just to cap it off, just note that if A is closed, it contains all of its limit points already. So the set of limit points of a closed set is just equal to the original set. Which, for example, if you take the closure of the open interval, 0, 1, you just get the closed interval from 0 to 1. If you have an open ball, centered around V, radius R, then the closure is just the closed ball, where that inequality is no longer strict. So here you can see why we had the bar notation from before on closed interval on the closed ball. And that's it. We're gonna look at some more properties of closures in the next lecture. Thank you.